First of all, you need to save this file as a step file. Go to save as, you can see STL file or step file. Step AP203 file is suitable for this Ansys simulation. Now you can open the Ansys workbench. I use Ansys workbench. Now go to Fluid Flow Fluent. Double click on that. Go to geometry and you can rename this file as Convergent Duct. Go to geometry and right click on that. You can see that import geometry and go to browse. Here is my Convergent Duct step file. You can open that one. Now go to mesh. Now this is our Convergent Duct we designed using SolidWorks. Now we have to mesh this Convergent Duct for the small segments for our simulation. First go to mesh, generate the mesh. But I need to convert this mesh into very small segments. So go to sizing, select fine and quality. Smoothing should be high. Now again you have to update the mesh. Now you can see that our machine part is completed. Our next part is we have to name our sections, input, output and other boundary conditions. For that you can go to insert. First right click on this mesh, go to insert. You can see that inflation. In inflation you have to select this whole body using this feature body. Select on this one and apply. This is a body. Now again go to face. Our boundaries, this is our boundary surface. This one was also boundary, this one and this one, but this one and this surface is respectively input and output, so we can name those surfaces later. Now apply. This is our boundary for the simulation. Now we have to name our input and output. For naming input and output, you have to select on the required surface. This is our input, so click on the surface and right click. After that you can see create name section. This is our input and this one is our output. And again you have to update the machine part. Now you can close this machine window. Now you can see our mesh is completed. Go to setup. In setup file you have to select option as double precision. In the setup file you have to first select gravity on y direction, minus y direction, so in my y direction minus 9.81. Go to models, energy, I open the energy equation, and this is a laminar flow. Next go to fluid. Fluid type is water, and you can select water using database, water liquid. And now to go to boundary conditions. In boundary conditions, you have to give a velocity value and pressure value for this input. For that, you have to go to edit. This is not a, this is stationary wall. Go to operating conditions. Gravity is okay. Now go to type, and in this type you can see this is a velocity inlet. You can give the velocity magnitude about 100 meter per second, and this is constant. And initial gauge pressure in Pascal you can give 100 and 1000 Pascal. This is also constant. Now boundary conditions are okay, and go to and select output. You have to select the type. This is output is not a wall, that is a mass flow outlet. And mass flow rate of the outlet is about 10 5 kilograms per second. Now our boundary conditions are okay for the outlet. Now go to solution. In solution under method, you can see that gradient is least square cell based and pressure second order. Go to controls. Keep these values as default. Go to initialization. In initialization is standard initialization, and compute from input, and select on this initialize button, and go to run calculation. Give number of iteration about 100 iterations. Now you can calculate this simulation. Now you can see that our calculation is completed. Go to result tab and graphics, contour graphics. Select a velocity distribution of the input. Here you can see that velocity distribution of entire body, and pressure distribution. And now you can see that our solution is completed. You can close this one, and go to results. In result, you have to go to streamline 1, all domains, and start from the inlet. Variable is velocity, and number of points are 250. And if you need to make an animation for this velocity distribution, you can select on this streamline 1 and animate like this. Again, go to streamline 2, and you can change the variable as wall shear, both forward and backward directions, and number of points are 250, and apply.